Hi, my name is Rahul Kumar Singh. I'm a graduate student at ICTST IFR Bangalore. I'm going to talk about Lagrangian manifestation of anomalies in active turbulence and also refer you to Siddharth Mukherjee's poster presentation in this session, which really forms the basis of this work that I'm going to talk about. Active flows such as bacterial suspensions display pattern formation and chaotic dynamical states, which resemble inertial turbulence. These bacterial flows are described by the generalized hydrodynamic equation, where the coefficient lambda of the nonlinear term tells us whether the bacteria is of a pusher or a puller type. The higher order derivatives ensure pattern formation in these flows, while the last toner 2 term ensures energy injection into the system via the parameter alpha. We consider a constant density flow, which means that the flow is incompressible. I show snapshots of the vorticity field, which is the curl of the velocity field u, for two different cases of activity, alpha minus 1, and on the right, alpha is minus 6. So as alpha becomes more and more negative, there is more energy that is injected into the system, and hence the flow becomes more and more active. For high activity, we have elongated patches of vorticity, which are not really present in the case of low activity on the left. And these patches of vorticity I'm going to refer as streaks. The emergence of these streaks leads to rather persistent motion of fluid particles. This is clearly seen in the trajectories followed by these fluid elements. As you can see on the left black colored figures, the trajectories can be diffusive or they can be persistent if the fluid elements are lucky to be caught up in those streak regions. The persistent trajectories have longer straight line segments with smaller number of turns as compared to the diffusive ones. And hence these trajectories starting from the center of the circle reach to the circumference much faster as compared to the diffusive trajectories. And this sort of a behavior led us to quantify the first passage distributions where we calculate the distribution of the times when the trajectories hit the circumference for the first time. We plot these distributions for increasing radii of circles such as 8, 10, 15 up to 30. And as you can see on the insert of the left figure, these distributions follow an exponential behavior. But when plotted again against a scale time dr by r square, where r is the radius of the circle, these all these distributions collapse to a single plot, showing that the behavior is rather diffusive when activity is low, such as alpha equal to minus 4. But when the activity is increased to higher levels, such as alpha minus 6, you can see that for shorter distances on the which is shown on the inset on the right, the collapse happens when the first passage time is scaled by r to the power 3 by 2, which really shows that the behavior is anomalous for shorter distances. While again, if we go at to distances that are large or for large radii of the circles, again the classical diffusive behavior starts to dominate, and we again get a collapse for r square, which is again shown in the main panel of the figure on the right. This then leads us to the question that what flow features are responsible for such anomalous behavior. And we turn to the Okobovo's parameter lambda, which is very commonly used in studies of inertial turbulence to identify such flow features. Here, sigma and omega are the symmetric and the antisymmetric parts of the velocity gradient tensor. Omega is the vorticity, which is a measure of the rate of rotation, whereas sigma is a measure of the rate of stretching component of the flow. Then by definition, a large positive value for lambda will mean that we are in a vertical region of the flow. So what we do is we pick out our fastest and slowest tracers for all instances of activity, and we plot the distributions of the lambda values that they experience as they are advected by our active flow. So when activities are lower, which is shown in the figure A, the PDFs for both the fastest tracers and the slowest tracers fall on top of each other. So the inset shows even smaller activity -1, while the main figure A shows a bit higher activity alpha -4. But for both of these cases, the fastest and the slowest trace, the distribution of lambda for fastest and slowest tracers just fall on top of each other. And we have really shown the fastest tracers in solid lines and the slowest tracers in dotted lines. But when I pump up the activity higher, say -6, we really start seeing the difference in the distribution of the lambda values that the trajectories experience. The distribution, the right tail of the lambda distributions for the faster tracers are a bit subdued as compared to the distribution for the slower tracers. This means that the faster tracers are experiencing smaller relative lambda values as compared to the slow ones. So this hints to us that faster trajectories sample smaller lambda values as compared to the slower ones, while we also remember that the streak regions were marked by patches of vorticity. So then this leads us to define a criterion where we can identify these streak regions. And this identification is done by limiting lambda to smaller values while keeping omega large. And with this sort of a criterion, we show a plot of the vorticity fields. So what we show are three panels, A, B, C. The leftmost is the vorticity field. The middle one is really the plot of my Okubo voice parameter, and the panel C shows the vorticity field when filtered using this criterion. So as you can see, this criterion really picks out those streaks of vorticity, and then now with this sort of an identification, we are able to calculate the times spent by the fluid elements in these sort of streak regions and calculate the displacement while they are in those regions. And we then plot the displacement, the joint distribution of displacement and residence times when these fluid elements are inside and outside the streaks. And we can really see that while they remain in the streaks for very small times, their displacements are much larger. So the y-axis really shows the displacement s, the x-axis is the time they spent in these regions. And while outside the streak regions, the distribution is much wider, signaling that they take a longer time to cover similar distances. So here, ultimately, we have quantified that it's the streaks, the emergent streaks at emergent streaks at higher levels of activity that are really responsible for my anomalous behavior, and that is how I will summarize this talk. That the novel flow features, which we call streaks, they emerge in active turbulent flows at high activity, and these features are really not seen in inertial turbulence. And these regions really facilitate persistent trajectories, which ultimately lead to anomalous behavior. Thank you.